all of the ANOVAs. So we're going to start by clicking the button. There we go. So we'll start with why ANOVA. So when we're doing mean stuff, so we're still in the section where we're covering categorical IVs. So all of this is about having grouped IVs in some way. And if we wanted to just compare means two at a time, so t-tests are like the Noah's Ark of statistics. You can only do two at a time. You have a real limitation if you have, let's say, 4 means. So we can only do 2 at a time, and generally you're going to have more than 2 at a time. And that can only be used with 1 IV and 1 DV. So our studies aren't normally that simple. T-tests are normally done as post hoc follow-up analyses. And so we're going to get into the bigger analysis. So we're working small and getting bigger. So ANOVA, an analysis of variance, is a cute name. Compare several means. So why ANOVA? Because I have 3 or more means. Okay. It also can be used when you have 1 or more IVs. And so it is a extension of regression, which is a terrible phrase. It is regression. So everything we're doing this semester is least squares. It's all linear regression in one form or another. And so ANOVA is just a special type of regression. Just like a t-test is a special type of ANOVA, which is a special type of regression. So all of this is still least squares. So all the assumptions for least squares still apply. So why can't we just use lots of t-tests? That would be simpler, I think a lot simpler on everyone. Because you're gonna, once we run the ANOVA, you're going to be like, well, then we're going to follow it up with t-tests. So why don't we just mix the ANOVA and do the t-test? I'm kind of with you on that one. But the biggest problem is the multiple IVs. So if you want to look at an interaction between 2 IVs, that you can't really do with a t-test. But the biggest issue is a star next to type 1 error. That's the answer. I think this is one of those theory questions on the test. So why not lots of t-tests? As it inflates type 1 error. So remember, type 1 error is the probability of rejecting the null when you shouldn't. And so we're finding things that maybe weren't true. Okay. So I've got a cute graphic here. Let's say if we have 3 different groups. Oh, it's being fancy all on its own. There you go. So we could do 1 versus 2, 1 versus 3, and 2 versus 3. So that kind of analysis is called pairwise. So when we get to pairwise post hocs, that's what I'm talking about. Comparing every group to every other group 2 at a time. So pairwise means 2 at a time. Okay. So 3 groups is 3 pairwise, 4 groups is 6 pairwise, and as we get more and more groups, or more and more levels, you're going to have more and more t-tests to compare every one to every other one. And so what that does is it increases the error rate. So there's 2 types of type 1 error. There's family-wise and experiment-wise. And we kind of did this briefly before, but family-wise is usually within each hypothesis. So if I have 3 hypotheses, I'm doing the error correction on each hypothesis individually. Can't talk. Experiment-wise is all of the hypotheses at once. If you have 1 test, they're the same thing. But this formula here is definitely on the homework that I haven't made yet. Is how to calculate error rates. Okay. So it's 1 minus alpha, or 0.95, to the n. And I have it more over here. Most people talk about it to the c, to the number of comparisons. Okay. So alpha is what we're setting as 0.05. That's why we have alpha as 0.05 in g power, and p less than 0.05, which we're really doing is talking about alpha. So 1 minus alpha, which is 0.95, to the c, so the number of comparisons. So for 3 comparisons, okay, it would be 0.95 to the 3rd. If I can make this happen. There we go. 3 minus 1. Okay. So the type 1 error rate is now 14%. So instead of being p less than 0.05, or 5%, it's now 14%. If you get 6 comparisons, I think it's 27%. So as you add more pairwise comparisons, it goes up exponentially. It's a power function. Okay, so more levels, or more groups, means more type 1 error. Okay. So when I ask you what the type 1 error rate would be without a correction, it's that formula. So how many comparisons do you have? Fill that in for C. And in R, you can do that with the little caret icon. I'll show you today. So family-wise is across, that's not even English, a set of tests, missing the word of, for one hypothesis. Experiment-wise is the entire experiment. So if you had 3 hypotheses and 3 tests each, it would be 9. Most people correct for alpha family-wise because it's less strict. And we'll talk about how do I do that today. So we can't do t-tests. There's your why can't I do t-tests. Instead, we're going to do ANOVA. So ANOVA is regression. And most of the time when people look at it like an SPSS output, you actually get the regression box and people go, ignore it. And so if you were doing an ANOVA in a regression style analysis, the question would be, is the model good at predicting the outcome? So can I predict their mean score knowing what group they're in? Okay, with an ANOVA, because we're still using our mean as a model. And that's fine, but most people are more interested in like the second half. Are there differences in the mean based on which group they're in? So it's the same math, it's just really a theory question. So people do ANOVA as the not regression style, like the way that you look at it, because they're interested in looking at, if I manipulate this IV, how does it change the group means? Mathematically, those are the same, but like for understanding them, most people pick the second one. Right? So I manipulated this thing, did it change the groups? Versus, is this model good at predicting the outcome? So they are the same question, but we're going to do this traditional ANOVA style because that's what people are used to seeing. The cool thing about doing this in R is that you can run the ANOVA, it's always run the same way, and you can ask for the traditional output or the regression output. That's just a simple little change in the code, which is kind of nice. And then when we get to dummy coding regression, we'll come back to this is actually ANOVA in regression. Okay, so what does an ANOVA tell us? So we still have to have a null and a research, or null and an alternative, or experimental, whatever. Okay. So just like the t-test, ANOVA has the null hypothesis as the means are the same. So mean 1 equals mean 2 equals mean 3. And then the experimental hypothesis is somewhere something is different. Okay. And our null. So your goofy example for the day is different doses of Viagra and how that changes libido. Because that's too great of an example to pass up from the field book. And so the dosages of Viagra don't change libido. The drug doesn't work. Okay. Versus something is different somewhere. Some mean is not equal to some other mean. It might be that we find that 1 and 2 are the same, but 3 is different than 2 and 3. 1 and 3 might be different, but 2 and 3 might not be different. And so it's not quite that they're all different. It's that one of them is different somewhere. Okay. So ANOVA is sort of like the big, did something happen? And then all the post hoc tests are, where did it happen? So it's called an omnibus test. This is a weird word if you've never heard it before. That means overall test. So overall, is there a difference somewhere? It's kind of like a little magnifying glass. Can I find something? So it tells us whether or not the group means are different, but doesn't tell us where or how. Okay, so ANOVA's the first step, and then post hoc tests are the second step. Yes, everybody still good? Lots of quietness. So getting into a little bit of the theory, we're still doing this model idea. So each person's score is predicted by the model plus error. So this is their score on the DV, so the average score, and this is group. When we get into two-way ANOVAs next class, I think, I can't remember if we did two-way or repeated measures first, it'll be group plus group. So our model will have multiple variables in it. But right now it's just one group variable. And so we're still trying to come up with a way to test if the ratio of variance, good variance to bad variance, is better than chance. And that's the F ratio. I remember the first time I learned this, the way I remember the difference was F, this was hard. A million years ago. They're not really that hard. But the first time you hear about ANOVAs, it seems like, what's going on? So we're going to come up with a ratio of good variance to bad variance. So that's systematic variance to unsystematic variance. And that is the same idea as T. Okay. Oop, I can't spell. So T and F are the exact same idea of a ratio, good to bad. It's just the math for them is different. So we did mean minus mean over standard error in some form, a couple different types of standard error. But I can't really do mean minus mean minus mean, because I don't know what that stands for. This is still going to be standard, some form of standard error on the bottom. So I have to figure out a new solution for the mean minus mean issue. That's what we're doing today. So the F ratio is not that different than T. Actually, from going from T to F, you just square it. So if you have two groups, T and F are the exact same answer, except it's T squared is F. Which comes really in handy if you're trying to understand somebody's results. But back to theory, not to math yet. So if a model explains a lot more variability than it can't, so if the good variance is a lot more than the bad variance, then we would say something happened. So there was a significant effect. So we still want these numbers to be very big. The cool thing about F is it's never negative. So F is always squared. So I like F a little better because I don't have to deal with the negatives, essentially. So back to that, I forgot to put the picture back in, but if you remember from last time, we talked about the removal of the brain. So we had the instructor that taught a class, and then the instructor where we took out their brain. It was the funny GIF that was moving around. So the variance created by our manipulation, so the removal of the brain from that example, or in today's example, the different dosages of Viagra. The variance created by unknown factors, so natural libido, testosterone, people are people, so they're all slightly weird. That's unsystematic, that's bad variance. And we're trying to create a ratio. Okay. Oh, I don't know what I mean by drawing. This. Okay, so it's a ratio of good variance to bad variance. I have no idea what I was thinking of there. Okay. The problem is that formula is not this easy anymore. Lame. Okay. So what we're going to do is calculate 3 different types of variance. And I have them broken down. Tell me I have the pictures. Yes. 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 Okay, good. I was afraid for a second these were the old notes, but they aren't. So we're going to calculate how much variability there is just overall. Okay, so that's going to be sum of squares total. So SS has made a reappearance. We talked about it at the beginning of this semester as sum of squares. So anytime you see SS, they're talking about some form of this, okay, which was part of standard deviation. So part of the standard deviation formula, the numerator, so x minus its mean squared, so sum of all the squares. So we're going to calculate total sum of squares, so how much variance overall is there in the study? Okay. And that's literally the variance of the whole DV ignoring the IV. So how much is just the variance to work with? So it's like kind of counting how many cookies there are in the jar before we get started. Then we're going to split that variance into 2 parts. Okay. So the variance is explained by either the model, it's good variance, or it's bad variance. Okay. And so this is like splitting them out into good cookies and stale cookies that you give to your friends. Or give away, I don't know. I'm hungry, so cookie examples. All right, we're splitting this into good variance and bad variance. So how much of it is explained by the model? We're going to call that sum of squares model. Okay. But, warning, in any version of any output from any one of these programs, it won't say model. It'll say the name of the IV, because our IV is the model. So when you're looking for this in the output, it's not going to be labeled as model. It's going to be labeled as the name of the IV. So in this study, dosage. And then we're going to break that into sum of squares, error, or residual. And you'll almost always see it listed as residual. Okay. Residual or error, one of those two. Okay. So we got our total, breaking it in half. And that's what this picture is for. Okay. So we're taking that total variance in the data, and we're breaking it into two pieces. Okay. So variance explained by the model and variance unexplained by the model. Okay. So if the experiment is successful, then sum of squares model will be greater than sum of squares residual, with the caveat that you can't look at those numbers. Okay. So sum of squares is only half of the problem. Right? We have to get also the fact that these are different numbers, are calculated in different ways, and we'll get to how in a second. So we have to calculate basically variance to variance, and so you can't just look at them directly. Okay, so we're going to go from sum of squares to error, and we got to figure out the degrees of freedom. So they're different for each one. The other thing that I've uploaded online that I don't know if you want to use it right now, but I have this F-table explain thing. It's on Blackboard. And I have kind of, because we're about to get into how are all these calculated, I have what I want you to get out of it. Okay, because you don't have to remember the formulas, because and I have that for the entire next section, because I've done that. We did this last year. So we're doing this first one way between subjects right now. If you want to look at that. By the way, it's online. So let's start with total. Now the odd thing is in the output in R, it doesn't show you the total. So total is only used every once in a while. But remember, sum of squares total is model plus residual. So it may not show it to you, but it's mainly because it's repetitive. So we've got our model. In this example, it's dose. Our residual. And down here we've got total. So we're making what's called a summary table, or an ANOVA table. If you've run any type of analysis before, you've seen one of these. So let's start with total. And we're not totally going to do this by hand because math, but kind of show you piece by piece before we run it in R. So we're testing the effects of Viagra on libido. We've got three groups. We've got a placebo group, so for a really traditional control group, a low dose and a high dose. And then we're measuring their reported rates of libido. Okay, so we got our model is going to be the mean of each group. So we're using group and their means. And our error is what we're working on trying to figure out how to calculate. Okay. So here's the data. And this is the SPSS data that's online. So we'll have to remember how to upload things in SPSS again. So practicing that skill again. So we have a mean for each person, so we have 5 people in each group, and then it shows you the average for each group. So libido is going up over time, which we would hope would be true, not time, dosage, which we'd hope would be true. I have variance and, standard deviation and variance. Okay, so those are just some summary statistics. So how do I get the total variance? So I plotted each person. You wouldn't normally do this way. It's really just to show you like what's going on. So each one of these is a participant, and this is their score. So I have them grouped by what group they were in. So here's our placebo group, our low dose, and our high dose group. So it makes this nice, pretty linear upward trend because it's made of data. And then bars here represent the mean. So I have 3 different means, and this is to show you this is really a linear model. Like testing these would be a linear question. So is this group actually the lowest? So this one compared to this one, compared to this one. But anyway, the black line here is the grand mean. Okay, so it's the average of all the averages. And so I would test each person's difference to the grand mean. So their little dot here to the black line. Okay, so I want to know how much variance is there overall. Okay, so how much variance am I starting with? And all these slides are super fancy. So they will do whatever they want to do because they're possessed. And So where do I start? If I want to know how much variance there is overall, so this is total variance, I'm actually going to use the exact same standard deviation formula you learned a while back. Okay. So x sub I is each person. So I've got people. Okay. So I'm take each person and subtract the overall mean. So this is the grand mean. This is the mean ignoring groups. Okay. So it's the average of the averages. Well, that sum all up squared. Okay. This is actually just standard deviation. So if you calculate a standard deviation on the column ignoring groups, that would be the sum of squares. But you'll notice we'll never take a square root. So you can't actually calculate standard deviation. I lied to you, it's variance. So I'm calculating the variance for each one. And then possess slide. There we go. And so this shows you just a couple of different ways to calculate it. But that n minus 1 is actually degrees of freedom. Remember that here. So we also have a total degrees of freedom. I'm not entirely sure why, because we never use it. Never. Ever. That I'm aware of. But it's a thing. So I think an important note to sort of stop and make a distinction between is big N and little n. So big N is the total number of people, participants, lines, whatever. Little n is people in each group. So we've got big N minus 1 down here because it's total number of people minus 1. Okay, 15 people, that would be 14. So sum of squares total is the total amount of variance we're working with. Okay, so it's this formula. So each person minus the grand mean squared. Yeah, everybody okay? Yes, that should make sense. So total amount of variance. Now I'm going to take that variance and split it in half. Oh, fancy slide. What's it doing? There it goes. That does not look right. I tried. Okay, so it's each person minus the grand mean. So this black bar is the grand mean, and then it's to each dot minus off center. Is everybody else's sort of off kilter? Mm-hmm. Okay, sorry. The slides were acting funny, but I didn't realize it was going to look funny. But imagine everything moved this way a little bit. So it's each person minus the grand mean. We've talked about degrees of freedom before, but degrees of freedom are the total number of values free to vary. So we have to take away 1, and we talked about this as like, I know I don't get this perfectly, so I'm going to minus 1, so I don't underestimate variance. Or you're taking away 1 because you have to calculate the mean. Okay, so it's the amount of scores that can change and keep the same grand mean. So we have people minus 1. So remembering that this is total number of people. All right. Oop. Forward. So x sub I with the bar on it means group minus the grand mean. So what we're doing is we're finding a solution to the m minus m problem. Okay. So I can't put that on the top. That's not a number that I understand. So -2 wouldn't mean anything to me. So instead, we're going to calculate how different each group is from the grand mean. And then this is where I'm going to draw my fancy picture. So, let's say we have a continuum of libido. And our low dose group is here, our none placebo group, our low dose, and our high dose. So they each have their own mean. What we'll do is first calculate the grand mean. And to calculate sum of squares total, we took each person minus the grand mean. And that hopefully makes sense. Now that I'm on the right track, we're taking each mean minus the grand mean. So we're figuring out how far away is each group from the grand mean. And you want them to be far away. This is good variance. And that means that the means are spread out. So this would be an example of the null is false. So we should reject. Statistically significant, if you will. Because the means are different from each other. They're spread out. If the null were true, we would get three little groups right together. So their good variance would be very small. Does that help make it a little clearer now that I'm saying the right words? Alright. So we're trying to figure out how far the spread is around the grand mean for model. Because that's how much your IV has made a difference. So the IV is what's pushing the means apart. So each group minus the grand mean, or level, if you will. It's multiplied by n because you have each person in that group. Okay. So back to my Oprah thing. You get some and you get some. So we have to count for each person in the group as well. Okay. I don't feel like that's quite as important because nobody ever does these by hand. As long as you're getting that each group is different from the grand mean. And that is what this possessed slide is trying to show. So how far is the red line and the green line and the blue line from the grand mean? So for degrees of freedom for that one, it's a little different. Now we're not dealing with people. We're dealing with levels or groups. So we're only using three means. And since we're only using three means, the degrees of freedom is going to be 3 minus 1. So it's the number of values you use minus the number of things you have to calculate, so the grand mean. So I can change 2 of these values and keep that same sum of squares. Okay. So anytime you see k, they're talking about the number of levels or the number of predictors. So it's going to be 2 here. So it's levels minus 1. Let me keep going levels here. So that's how different is my group from the average. And the degrees of freedom for that is groups minus 1. Now for the one I wanted to say a minute ago, residual. If I can tell how far apart the groups are based on the IV, I don't know why people vary within their own group. So that would be how much they vary from their own mean. So within their own group. So I don't know why there's variance within people's groups. Instead, I want to know more about the variance outside of the group. So sometimes this is called between subjects variance, or between groups variance rather, because it's how much they vary between groups. And this is called within groups, so how much they vary within. But then that's really confusing when you get to doing between subjects designs and within subjects designs, and you're just like, wait, what? So calling this model variance, how much do the groups differ versus residual, helps with the naming issue, so that the names don't all sound the same, because they are for a while. So we're talking about a between subjects design. Everybody's in their own little group. Repeated measures is in a couple weeks. And so good variance is how different are the groups. Bad variance is how much they vary within their own group. So why are some people different than others within that one mean? And that's unsystematic. I don't know why people vary from each other. Okay. I do, because they're people, but we don't have a variable to explain that. So this time it's mean minus my group mean. Okay, so person minus group. Let's go level. So each person minus their own level mean. So that's standard deviation, or variance, right here. Okay. So that's the traditional form of variance. And so all we've really done is modify how we're calculating variance. So this is all different types of standard deviation variance, except in the total one we ignore groups. In the residual one we include the groups, so we're subtracting them from their own group. And then in the model one we're using groups as people. So each group gets subtracted from the grand mean rather than each person. So after some fancy math, what happens is that this residual one is just a total variance within groups. So you just add up all the variances. Right, and that is how much they vary from their own group. Ridiculous slides. All right, so for the degrees of freedom for that, yay, math. It's degrees of freedom for each group added up, because it does have to equal this total. So if I have levels minus 1, I have 2, and the total is 15 minus 1, I got 12 floating around somewhere. And that's because it's n minus 1 plus n minus 1 plus n minus 1. So this bottom half is a t-test. Right? It's n minus 1 plus n minus 1. Add them all up. So for independent t, we did n minus 1 for group 1, n minus 1 for group 2, and we added them together. We saw how different each mean was. And then we calculated standard error, which is how different are they from their own groups. And now we've just magnifying that to add extra groups. So we're expanding the t-test, basically. All right. So do those two add up together? Yes, because otherwise this would be a terrible demo. Right? So sum of squares model and sum of squares residual always add up to total, unless something has gone really awry, or you're trying to do it by hand, because I can't math by hand anymore. But that's because we're taking total and splitting it out. Here's the good half of what you have in your jar, and here's the bad half. But I can't compare these directly, because they have different degrees of freedom. So the real problem with looking and saying, well, model variance right now is less than residual variance and having a small panic attack, right? Can't do the ratio directly, because this model variance is based on 3 scores, and residual variance is based on 14 scores, or 15 scores but 14 degrees of freedom. And so I can't just say model's less than residual, life is over. Instead, we have to calculate mean squares. So this is called mean squared error. Most people just call it mean squares. People sort of drop the E, but this is mean squared error. So you'll see that listed as MS. And it's sort of akin to calculating standard error. So remember, we would take the standard deviation, we would divide by the square root of n. Sort of similar to that idea. But now we're taking each variance, each sum of squares, and dividing by its degrees of freedom, so they're all on the same scale. So this one's only based on 3 scores, and this one's based on 15. I'm going to divide by those degrees of freedom to allow me to compare them. So you add going down, divide going across. So it adds this way, divides this way. Had a brief panic attack. Does divide have an E? Yes? Today it does? Okay. Wait, what? So sum of squares divided by degrees of freedom, but only for model. Sum of squares divided by degrees of freedom. Okay. And only for residual, nobody does this. Okay. So there won't be anything in these boxes. Okay. There's a reason I'm showing you this in this layout. So mean square for your model, sum of squares divided by degrees of freedom. So that's standard deviation, variance, right? So remember, it's always sum of squares over df. And we're not going to square root any of this. So it's technically all variance, because you don't take the square root, right? Remember, standard deviation and variance, 1 squared. So that's why this is called analysis of variance instead of analysis of standard deviations, because ANOVA has a better ring than ANOVA, right? I don't know. It's just called analysis of variance. So divide. So I got 10 points versus now 2 points. So when we account for the number of scores that went into the calculation, mean square model is much bigger. So essentially what the purpose of a mean square column is to account for the fact that this one's only based on groups and this one's based on people and evening that out. So the F ratio, to get to the very end, the number you're most interested in is here. Okay. So it's mean square model divided by mean square residual. Oops. So these two divided to that one. And that is how we deal with the mean minus mean problem. So that mean square model is an overall variance based on how different the groups are, whereas mean square residual is how different are the people within those groups, so the stuff we can't account for. And what I really want you to get out of all that math and numbers is this basic idea. Stop. Hold this up. So model is how different are the groups. Residual is how different are the people within their own little groups. And total is how much variance do I have to work with overall. So people minus the grand mean. And then the point of the F ratio is model variance to residual variance, controlling for the number of things that went into it. And so that's what the degrees of freedom come in. Yeah. So this table might appear on the test. Well, unfortunately, we're going to add 2 more of those tables before this is over. Okay, so there is the final table version. So I filled in the numbers this time instead of the words. And generally, most people don't even look at the rest of the numbers until you realize you have to calculate R squared. And you just go straight to F. Okay. When we do this in R, it will have the module column and the residual column, but no total. So remember that it adds going down. So you can create the total by just adding. And then it'll also give you P. So it'll give you the exact P value for that F. Okay. So let's talk about an F table. And I don't think I uploaded one, did I? I'm bad at this. Did I? No, I have the explanation table.
Oh, sorry.
I don't think I have the actual F table.
You have a comparison chart if you want to do things.
No, that's later. I'm bad at this, like I said.
No, there's an F table explanation.
Nope, that's the Word doc.
Oh, never mind.
I know there's one online. Oh, wait, there should be one in last year's class. That might be a little faster. So you guys think you have a lot of courses on Blackboard? Oh, no, that's not right. That's way too ugly to be the right course. I am nothing but crazy about the way my courses look. 3. There it is. All right, so notes, materials. F table. Where's the F table? Ah, there it is. Okay, so an F table, which I will put on Blackboard right now. Look, I managed to get here and get dressed this morning. That's about all you can ask of me. Okay. Oh man, Blackboard is slow. Alright, so now you have an F table. Yay! Okay, so if you hit refresh, you should be able to open this thing. Now, okay. So an F table, if I were to look this up by hand, which I finally last night, thank God, found a package plugin that will do the post hocs for us without having to do them by hand. Huzzah! It was such a struggle yesterday. But if you ever were having to look up one, somebody just gave you F, or you're looking at somebody's research paper and you're like, there is no way that's significant. They're making things up right now. Here's how you would look it up. So the way that it works, right, is numbers going across the top are the numerator. So the numerator, since this is numerator and denominator working its way across, so degrees of freedom for the model going across the top. So we would be looking in the 2 column. The numbers going down the side are the degrees of freedom for the denominator or residual. Okay. And it's clear, like, once you realize you don't have 14 going across here, which one's which. Okay. So you go 2, and then 14. Okay. And then I'm going to do 0.01. So my cutoff F score is 3.74. We talked about this last week as the mystery machine bust. Same idea. So what we've done is we've taken T. So here's T. Okay, we talked about cutoff scores. So we had a little bus, and it could decide to go either way. We took that whole thing and we folded it in half. So if you square all of this, what you'll get is the F distribution. And a marker that might not work. That's not any better. So T squared is F. And remember that T is also Z. If you have enough people, T becomes a Z distribution. So all of these statistics seem like they're very different. I'm trying to get you to realize they're actually the same thing, just slightly different versions of the math. And so an F distribution only has one cutoff score to make this 0.05, which we said was 374. So 2 degrees of freedom, so 2 groups, 3 groups, 14, 3.74. And so your car only has one way to go, because this is all variance. Variance is all squared. It's all positive. So T squared F. The F distribution mostly is centered over 1, where the ratio of good variance to bad variance is equal. I can't remember if it's this class or the other class, but if I ask you what would the ratio be if good and bad variance were the same, it's 1. Okay. So if all of your good variance is the same as all of your bad variance, nothing happened in your experiment. Okay. So F statistics have to get much bigger than 1 to be significant. Okay. So if you're looking at a table, even if you had 1 million groups and 1 million people, you can go to the end. Oops, that's chi-square. Okay. The smallest your number gets normally is close to 1.96, right? Because at the very end, it's going to end up going back to Z, or the square root of 1.96. Okay. Wait, 1.96 squared. Oh, long day. Okay. So the smallest your numbers get is close to what Z would be. Okay. All right. So we did this one. The model's going to be the one on the top, residuals down the side. So you could look up the cutoff score. I'll try 1 or 2 of those, just so you can see what should I have gotten to reject my null. So because it's all variance, F values are always positive. But stopping and thinking about what's the logic of this. If the values are small, if they're close to 1, you're saying that model and error are equal. If model and error are equal, basically your experiment didn't work, because the variance away from the gram mean is the same variance within groups. You can get an F less than 1, which means you got more error than model, which is really bad. Right? That means it's just all noise. If the model is greater than error, so you get 2, 4, 8, and you can get 3,000, it's really rare, but F can get really big. That means that there's a big effect. Okay, not big. We're talking about effect size in a minute. That means that something happened when model's greater than error. And that's the same as T. The larger the T value, the more good variance to bad variance you have. So these are all odds ratios at heart. So we want a bigger odds in our favor. I always feel silly saying that now. But we do want more of the odds to be in our favor. Okay, so bigger model than error. Okay, all right, so that's where